Välkomna. Jag tänker inte prata svenska. Jag har heller inte tänkt att snacka norsk. Vi är på TV, jag är i alla fall på TV, på internet. Så jag tänkte att ta resten av föredraget på engelsk, hvis det är greit. My name is Aslak Hellesøy. I'm probably most well known in the developer community for having created a tool called Cucumber back in 2008. I'm a programmer by trade, been a programmer for about 25 years. I got involved with open source development quite early in my career, also agile development around 2000. And I went to work for a company called ThoughtWorks, where there was a lot of activity going on at the moment, back in the days, and still is. So that's kind of where I learned a lot of tricks of the trade. A few years ago, I co-founded a company called Cucumber as well. We help organizations do behavior-driven development, improve their architecture, use Cucumber well, and so on. We also develop a professional tool called Cucumber Pro, and when I'm not doing either of those, I try to maintain the open source project. But I'm not going to talk about Cucumber today. I'm going to talk about testable architecture. So one of the things that I've come across when I visit various teams, teaching them practices like behavior-driven development, test-driven development, I see that a lot of people, they think these are really good ideas, but when they come back to their desk, back to their projects, it's really, really hard to put into practice all of the wonderful things that they've learned during the trainings. And that's often because they have to deal with a legacy system. Behavior-driven and test-driven development, it's about letting your code emerge in response to writing tests, but it also means that in order to do that, you have to have a code base that lends itself to that kind of process. And these organizations, they have another problem. They have this typical problem where the cost of change is somewhere around here, and they're worried that it's going to go skyrocket and become really expensive. Has anyone seen this one before? Okay. Now, why does this happen? Why does software tend to evolve, after a year, maybe after a couple of years, into this kind of state? The cost of change just becomes higher and higher and higher, and then one day the cost of the change is so high that it doesn't make sense to make the change. Right? Somebody has a feature request, we want to add a new feature, somebody makes an estimate, and it's going to cost 500,000 kroner to make this change, but it's just a tiny change, adding a text field somewhere, but we realize that, the financial gain we're going to get from that is inferior to what it's going to cost to build it. What happens in that case? Well, we scrap the system and we do a rewrite, right? Or in the worst case, the company goes out of business. So why does this happen? Lots of different reasons, right? But some of the common reasons are you have no tests or really slow tests. And because you have no tests or slow tests, it is really risky to modify the code to add this change. You don't know if you've broken something. There's also poor knowledge in the team. Maybe the people who wrote the software initially, they've all left, and now there's a new team developing the software, maintaining it. They don't really know how to make this change in a safe way. There might be a lot of financial risk involved, other kinds of risk, and quite often the code is just a mess. Maybe you know where to change it, but you're looking at this and you see that, well, if I'm going to change this piece, I have to change, a big part of the system. So these systems, they have what I would call the opposite of a testable architecture. They have an untestable architecture. whenever they make a change, it is really hard to verify that you made a change that doesn't break the system. So what I'm going to talk about today is some techniques that you can hopefully use to make an existing legacy code base more testable, or if you're starting from scratch, you can maybe use some of these techniques. Always a lot easier when you start from scratch. That said, I do not recommend the approach of rewriting an existing system. It's usually almost always better to refactor it. So, what do we mean by testability or testable architecture? Well, after having been working with tests for nearly 1.5 decades now, I've come to value 3 qualities of tests. And they are, first of all, they need to inspire confidence. You have to trust your tests. If you have tests that you can't trust, what's the point in having tests in the first place? So if you come in the morning and 20% of all of your tests in your continuous or nightly build are broken, you don't have confidence in your tests. And this has a really toxic effect on team morale. People stop trusting the tests. They basically lose their value, right? So you have to have confidence in your tests. The second quality is speed. I'm going to talk a bit about speed. They have to run really, really fast. And by fast, I mean within a second. And I know some of you are just shaking your head, that's never going to work where I work. But I'm going to try and convince you that it might. Finally, they have to be low cost. Kent Beck has said so. Kent Beck is the inventor of test-driven development. He was asked once if he always write tests, and he said, no, I don't always write tests. I'm not paid to write tests. And if we spend a lot of the time when we're working on a system writing tests, that's time that we could have spent building the system instead. But unfortunately, lots of teams, they end up with test suites that are really, really costly, and they're costly for various reasons. Well, they can be costly because they're slow, so they just take a long time to run, that's one thing. But they can be costly to write. If you have an awkward system, then it might take a long time to write the tests. And you build up lots of tests and they start failing. Now you spend a lot of effort maintaining the tests. Sometimes your software breaks and it takes a while before the tests tell you that something is broken, and you can spend an inordinate amount of time just diagnosing why is the test failing. So that's a cost. This particularly applies to large test suites that go through the entire system. When they fail, you don't really know where the problem is. So we want the tests to be cheap to maintain. We don't want to spend most of our time developing or maintaining or fighting with tests. And I have a theorem. It's a very unscientific theorem, but my theorem is you cannot have all of these 3 in the same test. So, you cannot have a test that gives you full confidence, that is super fast, and that is super cheap. You can, however, have a test that is very fast and low cost. It's easy to maintain and write test. It's very, very fast, but it won't give you full confidence. It will just give you a tiny bit of confidence about a tiny bit of the system. So what I'm going to show you is how you can have different kinds of tests that each have 1 or 2 of those properties, and when you put them all together, you will have all of them. But each individual test cannot satisfy all of these properties. That's Aslak's theorem. Okay, so we're going to talk a little bit about speed. Does anyone know who Jakob Nielsen is? Jakob Nielsen is a well-renowned user experience guru. He's written many books, and a lot of the things that you do on your phones or on your computers is inspired by research and things that he's said and written. And in 1994, he wrote a book called Optimizing Application Performance. And in this book, he talks about 3 time limits that are determined by human perceptual abilities. Now remember, this is a book about user experience, and he's talking about the psychology of user experience. And the first time limit that he talks about is 0.1 second, 100 milliseconds. At 100 milliseconds, or below 100 milliseconds, or 0.1 seconds, a user interacting with a user interface will feel like the system is reacting instantaneously when you poke it. You press a button, you see something happen within a tenth of a second, you will feel like it is instantaneous. Okay? So you don't need any special feedback within this time lapse, you don't need spinners or progress bars or anything, you can just take your time up to 0.1 second and display some feedback. The next time limit that Jakob Nielsen talks about is 1 second. So what happens in people's head at 1 second and beyond? Well, it turns out 1 second is the maximum length that a user's thought can stay uninterrupted. If you have a user interface that takes 1 second to respond, the users will notice the delay, but they can still maintain the thought of the activity they're doing. You know, you're browsing you're checking your email or something, you're tapping around. If it takes more than a second, your mind starts wandering somewhere else. Feedback isn't necessary within 1 second, but the user loses the sensation of operating directly on the data beyond 1 second. It feels like there's a lag. The user starts to feel a little bit annoyed, a little bit anxious. The third time limit Jakob Nielsen talks about is 10 seconds. And this is the limit for keeping the user's attention focused on the dialogue. If you're doing something in a user interface and it takes more than 10 seconds, guess what happens? You lose your patience. You start reading your mail, you go on Twitter, you go on Hacker News, maybe you go and grab a cup of coffee with somebody. And beyond 10 seconds, it's crucial to provide feedback to the user about how long the computer thinks it is going to take. Otherwise, they don't know. I don't know if this is going to take 15 seconds or 2 minutes, or even longer. And a friend of mine, Josh Chisholm, he's the one who presented these ideas to me, that Jakob Nielsen has said this about user experience. But what about programmers and interacting with the code? Maybe this is transferable to the activity of coding. What happens if you're programming and you get feedback within 0.1 second on the code that you've written? You can get in the flow. Has anyone here been in the zone? Raise your hand if you've been in the zone. Okay. So the zone, being in the zone, for those of you who haven't been there, that's when you lose completely track of time and space and everything. It's just you and your head. And you can't really describe what the sensation is like. And you can keep this, if things go beyond 1 second, it's really, really hard to stay in that zone. And what's the most important feedback that we get as programmers? Well, there's different kinds, depends on what we're doing. Compilation is one thing. If it takes more than 10 seconds to compile, then we're off to social media again and grabbing coffee. If the tests take more than 10 seconds, same thing, right? We don't know whether the code we've written is good or bad. And this is why it's so crucial to keep tests fast, because beyond 10 seconds, productivity of developers is severely hampered. you can never get in the zone, right? If you have to wait 10 seconds every time you change a function. Now, there are more time limits, and these aren't Jakob Nielsen's time limits, those are mine, and I'm sure some of you will agree. After a minute, you can't really do test-driven development anymore. If it takes a minute before you get feedback from the test, you just stop doing TDD. Because you're wasting too much time waiting for the test, so you just revert to the old way of coding where you're just coding, right? And then you'll do a little bit of ad hoc testing every now and then, maybe rely on the CI system. So if it's 10 minutes, then you don't even do the ad hoc testing. Maybe you run the test a couple of times a day at this time. But you can't run your tests more than, I'd say, maybe 5 or 6 times a day if it takes 10 minutes. If you run it more often, you don't get anything done. So at 10 minutes, you basically have to rely on continuous integration to give you feedback whether you've broken something. And then when you've broken something, whoops, you're out of the zone and you have to go back and fix it. 1 hour, this is where you stop running the feature branches that run for days and weeks and months without being integrated. You can have continuous builds if it takes this long, but you can't really have continuous integration because integration is just too hard to do when the feedback loop is that long. If it takes 1 day to get feedback, well, that's the situation where you come in the morning and 2/3 or a third of your tests are breaking, or maybe just 10%. You run a nighter build, you're starting to get into a really bad place. And a week, if you have to wait a week before you get the feedback, we're talking a whole different class of problems. Now, this is an organizational problem. This happens in organizations where you have programmers writing the code and testers testing the code. And you have this kind of us and them mentality. So a testable software architecture cannot fix this. Right? This is a cultural problem that you need to address in a different way. This is where you have lots of bugs, lots of rework, sprints always run over time, because at the end of the sprint you realize that half of your stories are not working and so on. So, sub-second TDD, that's the new kind of thing that I'm trying to get people excited about. How can we do test-driven development in a way that will give us feedback within a second so that we can stay in the zone and be happy, productive developers? Has everyone been here? It's amazing, isn't it? I mean, people who can do this, they are orders of magnitude more productive than other people, in my opinion. So, lots of people know how to write really, really fast automated tests using unit tests. You can just write a test for your class or your method, and you run it, boom, it's instantaneous. You get the feedback within, within 0.1 second. But what about full stack acceptance tests? That's a bit harder, because now we're not just talking to a single class or maybe a couple of classes, now we're talking to a whole system. So let's have a look at what a typical acceptance test looks like. So I made a simplified drawing here. If you can imagine, along the x-axis, you have the different functions or features in your system. So, I don't know, login, create an account, upload a document, comment on a document, generate some reports, all these different features. And along the y-axis, we have the different technical layers. So you've got the persistence at the bottom, maybe you've got some data access above, you've got some business logic, you've got some web server, maybe you've got some REST in between, and the UI at the top, right? So you've got all of these layers. And these are the kinds of tests that a lot of companies have. Particularly those kinds of companies who have this us and them culture where it's a different team that writes the automated or sometimes manual tests for the system. That's a different team from the people who write the software. The reason tests end up looking like this in those kinds of places is that these are the only tests that those people can write. You have to treat the system like a black box. You can't comment on a document before you've created an account and logged in. You have to do this over and over again for every test, so they can become really long journeys. And we don't know, those people don't have the skills or even the authority to connect the test to, underneath the UI, because they don't have access to the code. Quite often you need to change the code before you can connect the test. Oops, in the middle. So if you open this box, quite often it looks like this. You've got spaghetti. And why does it look like spaghetti? By spaghetti, I mean a really bad, tightly coupled, ugly code. Well, it quite often looks like that because the developers themselves don't refactor the code. They don't refactor the code because the tests are too slow. We were talking about a feedback cycle of 1 day and above. There's no way these people are going to make structural improvements to the code as they go along. They're just going to add more features to it, and you have this cost of change curve that goes through the roof eventually. So you've got an unmaintainable code base and a slow test suite. Now what we can do instead is to make those fast, we can have tests that look like this. So what we've done here, we've removed the top layer and the bottom layer. Basically we've removed the user interface and we've removed the database. Now if we manage to write a test like this, it will give us confidence about everything that is within this green box, right? It will give us confidence that this is working. It won't give us confidence that we're integrating with the database correctly, because we're not testing that in this test. And it won't give us confidence that the user interface is connected to the server, to the business logic, but it will give us a lot of confidence about how we've implemented the business rules, assuming that they sit inside here. And these tests can be really fast. Have you ever thought about why tests are slow? Like, really, why are they slow? It all boils down to one thing. Yeah, I have to have some water while I think about what it is. Between each layer here, not every layer, but many of them, there is networking. There's a socket. There's a browser talking to a server. There is a data access layer talking to a database. And networking is what makes tests slow. And if you've got several layers of networking, they're each going to be really slow. I mean, we're talking a couple of orders of magnitude slower than tests that test software in a configuration where there is no I/O. Okay? So one of the strategies, and one of the things you should be looking for if you want to make a test suite faster, is to identify where is the I/O, where is the networking, or maybe where do I access the file system, because that's another kind of I/O. And sometimes do we have threads and sleeves and stuff like that, but most of the time it's I/O. So these tests are a bit faster because we have less I/O. Another kind of test that you can have is tests like this. So here we're not testing a user journey going through the system. This is more of a technical test. We're just testing that the user interface can talk to the web server, testing that the web server can talk to the domain layer, testing that the domain layer can talk to maybe the persistence layer, persistence layer can talk to the database, and I don't know, database doesn't run on disk space, whatever. This is what I call integration tests. Some of you might think that, hey, that's not an integration test. This is terminology, or this definition of integration test I've learned from J.B. Reisberger, a loud, very entertaining Canadian gentleman who loves to talk about tests. I recommend reading his blog post called "Integrated Tests Are a Scam." So this is not an integrated test. These are 5 different integration tests. They test the integration between 2 layers. Okay. These tests are really slow. Not all of them, but every one of them that cross the I/O have I/O boundaries. They're slow because there's I/O involved. So we don't check the fast box here, but they give us some confidence because they are basically telling us that, hey, at least we've managed to wire stuff up together. This layer is talking to the other layer correctly. We're just not testing it with everything else, but we've got these tests to give us more confidence about the logic. We've also got unit tests. Now, unit tests, I guess you're all familiar with. That is the kinds of tests that just test a particular class or a particular function, and they can run in isolation. You can use stubs and mocks to decouple them from the rest. So I'm talking about 4 different kinds of tests here. We have the unit tests like this. We've got integration tests that are tiny tests that just test boundaries between layers. We've got acceptance tests where you remove some of the most costly I/O layers, and then you've got the big end-to-end tests. 4 different kinds of tests, and they each have they satisfy these criteria differently: confidence, speed, and cost. Right. So you need all of these kinds of tests. You don't need the same amount of tests of each category, but you need all of them to have, to have a good balance. So how do we do this in practice? I mean, these are nice drawings, or maybe not that nice, but I'm going to try and show you now from a different perspective how you can actually do this. Is anyone here familiar with a guy called Aslak? Right. Has anyone heard of hexagonal architecture, or ports and adapters? So ports and adapters is an architecture pattern that he discovered, I guess. I think it was in the mid-90s. If you Google Aslak, hexagonal architecture, you'll find this article, and you'll see that he hasn't changed the page since he wrote the article in the 90s, or maybe very late 90s, so it looks a bit like the 90s. But the idea is you decouple all of the external devices, he calls them, from your business logic. So your system is unique, that's why it exists. It's got some unique business logic in there. But we figured out a way to decouple it from the external world. And the external world is things like a database, or some other web service that you need to call, or a user interface, or a message queue. The business logic doesn't have any tight coupling on this external infrastructure. It's a little bit like the ports and adapters on a computer. On the side of your computer you've got a USB, and maybe you've got a VGA, and you've got a power port. You can plug different things in there. The computer doesn't really need to know exactly what you're plugging in, as long as it conforms to the specification. So it's using the same idea for software. And if you're using an object-oriented language like Java or C#, these ports are essentially interfaces. It's an interface. So you can think of, well, this interface here is something that has, I don't know, some methods on it here, but in order to work, you need a concrete implementation of it, so we'll have a concrete implementation that talks to a queue. Here, you know, maybe this is an interface that has two methods on it, load, I don't know, load document and save document, right? Or load person and save person. But how, the fact that that's done through SQL, that knowledge is only in here. So everything that's inside the inner hexagon is completely decoupled from the outer world. It doesn't know how things get sent back and forth to those external devices. And this allows you to swap in and out other ports, which allows us to do some really interesting things. So if we want to do a complete end-to-end integrated test, it will look like this. You know, this is the first one that, you know, the big square like that. This is where we have a test that is connected to a user interface, maybe a mobile phone here. It goes through the network. There's some networking here as well between the test and the mobile phone. Talks to some REST API maybe. And then all this interesting business logic in here, God knows what it does. Send some messages through queues, store some stuff in the database, maybe call some web service. So this is a fully integrated test that will give us full confidence that everything is working correctly, especially if we have hundreds of them, or thousands of them. Unfortunately, if you have hundreds or thousands of these things, you're going to have to wait a few hours from you start them until they're done. So you can't rely on these kinds of tests alone. A lot of organizations do, because they don't know a different way to do it, and also they don't have ports and adapters, right? Because these things are hardwired. But they give you confidence, they give you the full confidence, but you don't need to have all your tests like this. These are the worst tests. Really they are. They are so slow. When they fail, okay, well, if this test fails, where's the problem? Anywhere, right? How long does it take you to find out where the problem is? Well, it takes a really long time. It can take days and weeks, sometimes months, right? I mean, you don't really know, depending on how big your system is. Has anyone ever worked with flaky tests? Tests that sometimes pass and sometimes fail? They are the worst. That's these kinds of tests. These tests are flaky because there are so many things that can go wrong. You've got asynchronicity going on here. You have some sleeps, make the test even slower. Sometimes the sleeps aren't long enough, so we get flakiness. You don't really understand the problem. Horrible, horrible tests. You need a few of those tests, but you don't need many. I mean, we work on a system that is, I guess, medium size, whatever that means. We've got a few dozen of those. That's it. We've got thousands of tests, but only about a dozen of them are these kinds of tests. So a different kind of test, that is an integration test. So this is an integrated test. Everything is integrated. An integration test is a bit different. That is a test that we've only connected to this class here. Or maybe we could have connected this. Actually, that's actually wrong. We should have gone straight into this light blue thing. Doesn't matter. We can run this one and only test the integration between our, the main logic here and this thing that talks to a queue. Is this test going to be fast? No, it's not going to be fast because there's networking involved. Is it going to be expensive? Is it going to be expensive to maintain and write? Probably not, because you're dealing with a very narrow interface here. You know, this is just about sending some stuff and perhaps receiving some stuff. it's a much easier test to write than this test, right, comparatively. So it's slow, but it gives us confidence that we've integrated this properly. You know, that we're communicating with the external device properly. We know we set the passwords correctly, the IP addresses, you know, all that stuff works. But it gives us a very tiny confidence just about this component, not about everything else. Remember I talked about, you know, there's the big square that tests everything, and then there's like another big square that isn't quite as tall, where we remove the user interface and we remove the database and maybe queues and stuff like that. So we can plug in a different adapter here without this stuff inside knowing about it. We'll call that a fake. And we can test the fake. So the fake isn't production code. This is part of our test suite. All the green ones, that's just test code. But this, if you do this, it can help you build confidence in the fake. Because you can run the same test that you ran against against the fake. Has anyone ever tried to run the same test against two different implementations of something? Right. So that's a contract test. It's called a contract test. You're basically testing not the implementation, but the fact that it satisfies a contract. Contract is between here. Now when you do this, if you run the same test against a fake implementation and a real implementation, that gives you the confidence to use this fake in other tests, which is amazing. Now, it's getting interesting. Now we can use those because we have confidence in them, they behave exactly the same way. We can use those for completely decoupled acceptance tests. Because our contract test gives us confidence that they behave the same way. So this is an acceptance test which tests all the domain logic, but without being slow, because there's no I/O going on here. So these are acceptance tests where you can run thousands in a second, at least hundreds. You know, these kinds of tests, they take between 1 and 10 milliseconds typically, because they're only CPU bound. Is anyone doing this? See? One person, maybe two. Nobody's doing this. I don't know why. It isn't that hard. You just need to know it's possible, and you need to maybe see some examples of how it's done. I'll show you an example. So you can have many of those. And what's even more interesting is that these tests here, you do this right, they can be the same as those tests. So you don't duplicate the test, you just run the same test in a different configuration, depending on whether you want speed or confidence. So developers on their desktop, to get this sub-second feedback and stay in the zone, they run these tests. And on the continuous integration server, you will run the slow, stodgy tests that give you all the confidence. There's the last time test that I haven't mentioned. Unit test, right? You still have these. Acceptance tests, they are the tests to give you confidence that you have the right code. That you have the right code to solve the right problem, the right business problem. Unit tests, on the other hand, they are there to prove that we have coded it right. Acceptance test for proving you have the right code, unit test for proving you have coded it right. It gives you a different kind of confidence. So you've got all these different kinds of tests, and you need all of them to get a good trade-off between speed when you need speed and confidence when you need confidence. And this is what, this slots right into the test pyramid. Test pyramid by Mike Cohn is a recommendation. about how many tests you should have of different kinds. It's not very specific about how you write those tests, but I've tried to be a bit more specific. So at the top here, you can have a handful of really slow, maybe quite brittle, end-to-end test everything. You'll have a bit more, but not that many, integration tests that just test the boundary between your domain knowledge and your cube or your database or whatever. And then you can have rather quite a lot of these. They can be the same as these. So what you can do is you can say, okay, well, we're going to have, I'm just going to pick it up, we're going to have 100 of these. So we're only going to run 10 of them in the full stack configuration. Okay. They can be the same test code. And then finally at the bottom you've got lots and lots and lots and lots of unit tests that test different components. You can have unit tests for all of the different layers testing the components. I'll give you a quick demo of what this looks like in practice. So a little node application. Just a to-do list. Not sure. Here. Right. Okay. Right, I need to move this over here. So do list here. Right. So to-dos are manual testing, right? Now I've got some automated tests as well. Let's try and run them. So what I'm doing now is I'm running the same test in different configurations. So I've got a hexagonal architecture with ports and adapters, and I'm running them in many different configurations, trading off speeds for confidence. You can see the last one I'm using Selenium, clicking around. So you see in the fast configuration where everything runs in memory, I run basically one test runs in 5 milliseconds, really fast. How many of those can I run in a second? 200. Or maybe even more when it kind of warms up a bit. Then I have a slightly slower configuration where I'm actually running with the user interface. So this is an application that consists of a server and a client, runs in the browser. The client, both the server and the client is written in JavaScript. So in this configuration, I actually run the UI and the server in the same process, and the test as well in the same process. So there's no I/O, but it's kind of like an integrated test without I/O. And then here I have another one where I add HTTP, and here I've got DOM and HTTP, and finally I go with the database, and this one is the full stack. So you see at the bottom, and they get slower and slower, but they also give me more and more confidence. So you see at the bottom here, these, whenever in the full configuration, it takes nearly 5 seconds, as opposed to 5 milliseconds. That's three orders of magnitude slower. That's what we're talking about when you have a full stack test.
Same test.
Same test. Yeah, running in different configurations. So it's basically like this, but in the fastest configuration, all of the adapters are stubs. In the slightly slower one, I've said, okay, well, we're gonna use one real adapter, and in the very slowest one, everything is the real thing. And if you have what's it called? Microservices. So microservices are very fashionable at the moment. Not everything is in one code base, so well, how can you do this? Well, microservices talk to one another, and if you manage to design your microservice in such a way that what one microservice requests from another, is the same as the input port and the output port of another microservice. You can connect them like this and remove all of the networking adapters between them and just run them in the same process. This works. This is easy to do if they're all written in the same language, because you can run them all in the same JVM or the same Ruby or Node or .NET process. It isn't so easy to do if you have a polyglot environment, obviously, because then you need, it's a little bit more complicated to do this communication here. But you can tear them apart and connect them via databases and queues and the REST interfaces and so on to run them in a higher confidence mode where you pay the price of speed. So that's it, really. If you want to take a look at that code base just to see how it's implemented, I will just Google to do sub-second, and if not, send me an email. I'll tell you where it is. So how do you go about doing this in an existing code base? Well, Jason kind of alluded to it in his opening keynote, I think. Somebody just has to be the first mover. Identify some kind of external system that your application talks to that is particularly slow or particularly flaky, and see if you can wrap that interface in your own interface. Right? So let's say, what was the Facebook integration? Right? I don't expect most of you to develop Facebook integration, but you know what it is, like logging with Facebook. Right? Let's say you have this in your app. So if your app has a direct dependency on Facebook's API, what you can do is you can break that dependency and say, well, actually, no, my application isn't going to know anything about Facebook. It's just going to depend on an interface that we invent, which is called login. And login returns true or false. And then our tests are basically just going to test how does the application behave in the case of true, how does the application behave in the case of false. And while we're testing that, we can plug in a fake login module that will always return false for Aslak and true for everything else. Right. So try and do it on one little corner of the application, get familiar with it, get some experience. When you've done that, find a mover on your team, bring them along, do it with another one together. You have to have patience and courage to do this, but when you get there, you can get back to what programming really should be like, and stay in the zone, and just write lots of code. Thank you.
Thank you very much, Aslak. Is there any questions? There should be. Or are you all going to do this when you get home?
So no questions, that usually means everything was just clear, or it was like, I don't know which one it is.
Regarding the fact that most applications are built up of different languages, and you had the branches here that you had the JavaScript server and the JavaScript client, right?
Yeah.
Yes. How would you say you should spend your time emulating other backends if your test framework is one language different than one part of the system?
So yeah, it's a good question. I mean, you won't be able So what you really have, right, is you can have two hexagons, one for your user interface and one for your server application. You need to test those things in isolation, but you can focus on defining a strict contract between them. There are various tools that can help you do that, like Pact is one popular tool, and there are various other ones. Well, I guess this is the case here, right? I mean, this is maybe written in Swift or something. So you'd have to have a different test suite for this and for this. But you can connect and test directly to this API here and pretend to be a phone, and then just observe what comes out at the other end. So you won't get this, complete holy grail of running everything in the same process, but you can still run pretty big chunks of it in the same process.
Any other questions?
Yeah, so I attended the workshop yesterday, so now I got a heavy dose of ports and adapters.
Sorry.
No, that's great. Is this the holy grail of testing, or are there other methods as well that could be just as helpful to know about?
Look, who am I to say? I don't know. This is the best way I've come across so far in my career. I'm sure somebody will discover better ways. There might be better ways that I haven't come across. I don't know.
Yeah, but in general, I mean, I assume you talk to other people about tests. So are there other people who feel like there are other methods that they like better than this one, that are, equal in...
What I see a lot is a different approach, which I don't think is a good approach, but is a very common one. And that is to, instead of replacing, instead of plugging in stuff like this, people plug in fake queues and fake databases and fake web services and so on. And there are even products that you can buy, either as SaaS or you can install them. And it might be a bit simpler because it doesn't mean that you need to re-architect your system or introduce this extra bit of indirection. And I guess that has merit in some cases. But now you have a more complex test infrastructure instead. So it's a trade-off. I haven't really used it that much in other approaches, but I know a lot of people do that as well. And you can get similar benefits from that. I think it boils down to taste a lot as well, and how much time you're willing to spend on adding. Let's not fool ourselves. There's a bit of added complexity here, right? To end up with a system like this, is that a price you're willing to pay? Some cases, yes. Some cases, no.
Thank you very much. I don't know if the architecture of this is testable, but for sure you will know when you're done.
Wow.
Thank you very much.
Thank you very much.